Okay, Assalamualaikum warahmatullahi wabarakatuh. Um, basically today we will continue with chapter 1, part 2. So in last week lecture, actually we already start with the chapter 1, part 2 lah. Okay, on the errors in measurement. Okay, so just a repetition of what you have learned in the last week lecture. So basically, we know that in any measurement, there will be error. So we cannot get exact the correct value, the exact value. Okay, when you do measurement. So that's why when we do measurement, usually there will be error tolerance. Okay. So for the measurement characteristics, okay, there are two types. So the first one is static measurement and the second one is dynamic measurement. So static measurement is when the process is constant. Okay, the target that we want to measure is constant or still. Okay, it doesn't move. Different to the dynamic measurement is where the target, the things that we want to measure is moving. Okay, the measuring a varying process condition. Okay, so for measurement, there are several characteristic or parameter that you need to know or to understand in order to determine whether the measurement is good or not. Okay, so the first performance characteristics that you need to know is of course the accuracy lah. Okay, so last week I already mentioned what is accuracy. So it's basically the degree of exactness, and the second one is precision. So different to accuracy, precision is actually the measure of consistency. So you can see from this figure over here, you can directly differentiate lah. What is the difference between accuracy and also precision? Okay, and then we can also calculate the accuracy and precision using this formula. Okay, so this formula is very important. So accuracy is actually the percent accuracy is 100% minus the percent of error, and relative accuracy, okay, or the absolute accuracy is actually 1 minus the expected value minus the measured value divided with the expected value. Okay, and whereas for the precision, this is the formula 1 minus value of the nth measurement minus the average value of measurement divided with the average of measurement. And the third characteristics is the resolution. Okay, so the resolution is actually the absolute smallest change that measurement system can measure. Whereas for the sensitivity is actually the ratio of the change in output to the change in input. And these are the formula that you need to use in order to calculate for the absolute error and also the percent of error. So in last week lecture, we have tried this example. Okay, how you can calculate using calculate the absolute error, percent error, relative accuracy, and also the percent accuracy using the formula that has been mentioned before. Okay, so next we also have covered on the types of error. So basically the error, we can divide it into three types of error. The first one is gross error, which is caused by human. Second is the systematic error, which is caused by the system flaws. And the third one is random error lah. So the cause of the random errors is unknown. Okay. So for the systematic errors, okay, there are three factors that are actually causing the systematic error. So the first one is instrumental error. Okay, so this one is caused by mechanical flaws. The second one is environmental errors. Okay, it caused by the changes in temperature, humidity, or even pressure. And the last one is observational error that is introduced by the observer's physical position. Okay, and then the random error is the error that is unknown. Okay, so last week we stopped here. Okay, we stop at this slide. Okay, so we will continue today for the dynamic characteristic. So last time in last week lecture, all the performance characteristic that I mentioned before, like um, accuracy, precision, and so on, that one falls under the static characteristic. Okay, so for the dynamic characteristic, okay, let me draw. Okay, for the dynamic characteristic, you see the industrial instrument is rarely measure constant condition. Okay, so in our daily life, usually the measurement that is made is actually dynamic measurement. We rarely encounter static measurement. Okay, so why? Because mass thermal capacitance or even electrical capacitance instruments rarely responds instantaneously. So there will always be delay. Okay. Okay. So how this target is actually moved? Okay. So for dynamic measurement, okay. So this value can move in three ways, or we say this as the variations in measured quantity. Okay. So this is variations in measured quantity. So the first variations is that the quantity, the changes can happen in step change. Okay, so step change actually looks like this lah. So this is the step. Okay, it looks like a step, so we call it as a step change. Okay, so this is the first one. The second variation is linear change. Okay, so the linear change is looks like this. Okay, so when one parameter increases, the other parameter also will be increases. So it is directly proportional. This it is steady and it is directly proportional with time. And the last one, this is a sinusoidal change. Okay, so I'm sure that everyone knows what sinusoidal actually means. Okay, so the magnitude actually fluctuates a repeating wave of constant amplitude. Okay, so how these instruments actually reacts, or the dynamic performance characteristics. Okay, so previously for the static performance characteristics, we have the accuracy, we look into the accuracy, we look into the precision, we look into the, what else? We have also the error, resolution, and also the sensitivity. But different to dynamic uh, measurement, okay, the to determine the performance, whether the performance is good or not, there are four parameters that we will look into. So the first one is the speed of response. Okay, how fast is the response? Okay, the rapidity in which the instrument notices and reacts to changes. The second one, we look into the lag. So lag is actually a delay. Okay, the delay before the system responds. So we actually call it as lag. The third one is the fidelity. So fidelity is the degree of reproduction. Means that how perfect the output actually mirrors the through the input. And lastly is the dynamic error. Okay, so this is similar to what we have for static uh, performance characteristics lah. Okay, we have error. It's just that for dynamic performance characteristics, we call it as dynamic error. Okay, so it's basically the difference between the true moving value and the measured value. Okay, so it's very important for you to know, okay, the difference between statics performance characteristics and also the dynamics performance characteristics. Okay, the next part, we will look into the statistical analysis, okay, for measurement. Okay, so when we do measurement, okay, it is good if we can use statistical analysis, okay, to actually um, to come out to see what happens in the data. Okay, so we have several statistical analysis. So the first one over here, the first statistics that we usually use is the first one is the arithmetic mean. So this one, I'm sure that everyone knows what mean value is. So it is actually the sum of a set of n numbers divided by the total number of data. And the formula is this one. So it's basically the mean value or the average value or the center. Okay, so if you look at the figure in this slide over here, so basically you have several data points. Okay, so in order to calculate the arithmetic mean or the center, you need to add all the points and divide it with the total number of data. So for example, after you calculate, you will get a value, which is we call as the center or the arithmetic mean here. The second statistical analysis is the deviation. Okay, deviation or we call as the distance. So deviation is actually the exact difference between one specific of data to the arithmetic mean. Okay, what does this mean is before this we have calculated for the mean value, which is the center, and deviation is actually the difference between each of the data with respect to the arithmetic mean. So for example, we have this data here. Okay, so I want to find the deviation for this data. So what I need to do is that I need to use the formula D1 equals to X1 minus X bar. Okay, so X bar, X1 is the value of this data minus the mean. So it's basically the deviation, okay, or the distance between this data here with the mean. So if we have, so over here we have so many data, okay, so each data here we can calculate their own deviation. Okay, so for example, if we have 23 data, that means we can have up to D23. data. Okay, so for example, if we want to find this d of this data, then you need to find the distance from this data with the mean value. Okay, so the next statistical analysis is the average deviation. So average deviation is the average value of all individual deviations. So previously you have the deviation over here. Okay, so like I said, if you have 23 data, then you will have 23 deviation up until D23. So when you calculate the average of the deviation, we call it as the average deviation. Okay, so the formula is you need to add all the deviation d1 plus d2 until dn and divide with n. Okay, the fourth one is the standard deviation. So standard deviation is the degree to which, sorry, standard deviation is the degree to which the values vary above the average. Okay, so this standard deviation actually define our region of doubt in the data. So the formula will be d1 squared plus d2 squared plus dn squared divide with n minus 1 square root. Okay, so now let's look at this example. So this example says that, so we have 10 readings, okay, 10 capacitor readings. So actually what happens is that, for example, in a laboratory, you want to measure a capacitor value. So we did 10 readings. Okay, so with 10 successive readings of a single capacitor, we don't get the exact same value. Okay, so for example, the first reading we get 1.003 microfarad. The second reading we get 0.998 microfarad. Maybe in the third reading we get 1.001. So the value actually changes because the capacitor has the error tolerance. So by applying the statistical analysis, okay, to this data, we can mathematically define the precise region where the true capacitors actually lives. Okay, so from this data, actually we can calculate or measure the mean or average value, the deviation value, the average deviation, and also the standard deviation. Okay, so for this one, this is very simple. So I want this to be as your homework. Okay, so please try this example and try and calculate the mean value deviation, average deviation, and standard deviation. So it's practically very straightforward. Just use the formula that we have introduced before. Okay. So the next part of chapter 1, part 2 is the randomness error or the Gaussian distribution. So as you can see in this slide over here, so we can see that errors practically uh, represented in a normal curve or Gaussian distribution. Okay, what we can say from this figure is that, so basically axis over here, this is the error. So you can see that the errors, it can be either positive, it can be negative. It's 50-50. Okay. There's an equal possibility of a positive and negative random errors. So this is what I said just now. It is 50-50. Okay. And all the measurements includes large number of small random and also distributed errors. Okay. So now let's look at the region of probability. So the shaded area here, okay, is the region of the probability. So the shaded area represents observations that differ from the mean by no more than one standard deviation. Okay, so for normally distributed data, this area here, okay, from negative 1 sigma to positive 1 sigma, the area here actually equals to 0.68 or 68% of total cases. So it means that 68% of the errors happens at this region. Okay. Okay, so this figure over here is similar what I've shown you just now. Is just that to tell you that from the so this part over here, okay, this part here, the inner zone we call as the inner zone, okay, from negative 0.6745 sigma to positive 0.6745 sigma, the area uh, or the region, okay, is actually equals to 50%. And then the mid zone, okay, from negative sigma to positive sigma consists of 68.28%. This is what I've introduced in the previous slide here. Okay, and then the outer zone from negative 2 sigma to positive 2 sigma, it consists of 95.46%, and the fringe zone from negative 3 sigma to positive 3 sigma, it consists of 99.72%. Okay. So the boundary here, okay, for the negative from the negative 0.6745 sigma to positive 0.745 sigma is actually consists of 50%. Okay, so for a single reading, VR is equals to 0.6745 sigma, and for mean reading, okay, we use RM. So Rm is equals to R divided with N. N is number of data minus 1 square root. Okay, so this is what we call as the probable error. Okay, R. The next type of error, we have the limiting error. So this is the probable error. This is the probable error, R. The next one, we have the limiting error. So limiting error, okay, what is limiting error? Is basically that for any instrument, okay, the manufacturer of the instrument actually already guaranteed that only within a certain percentage of the full scale reading. So they don't guarantee 100%. Okay. So for reading less than the full scale, the limiting error will be increased. Okay. So this is something that is very common. So actually, the measurement instrument that we use, basically the manufacturer actually only guarantee that the accurate reading is within certain percentage of the full scale reading. Okay, so what does this mean? For example, you have a 600 voltmeter. Okay, so the maximum here, you have 600 volt voltmeter with an accuracy at full scale is 2%, plus minus 2% at full scale. Okay, so we can actually calculate the limiting error when it is used to measure a voltage less than the full case, for example 250 volt. Okay, so for example this we said that this is an example. Given a 600 voltmeter with accuracy plus minus 2% at full scale. Calculate the limiting error when it is used to measure a voltage of 250 volt. Okay, so if you have this kind of question, okay, asking you to calculate for the limiting error, so the first thing that you need to do is to calculate the baseline error. So how to calculate the baseline error or the magnitude of limiting error? Okay, magnitude of limiting error, or we call as the baseline error. Okay, so to calculate this one, we already know that the error is plus minus 2% full scale. So the full scale is 600 volt. The full scale is 600 volt. So you need to find 2% from the full scale. So 0.02 multiplied with 600, you get 12 volt. Okay, so this is plus minus 12 volt error. Okay, so however, this error is actually when you calculate at full scale, meaning at 600 volt. But now you are measuring a 250 volt, which is much lower than the full scale. So basically the limiting error will be different. Okay, so what you need to do is that, okay, you need to take the magnitude of limiting error or the baseline error and divide it with the voltage value that you measured, which is 250 volt, and multiply with 100%. So basically, the limiting error that you get at 250 volt is equals to 4.8%. And this is much worse than the limiting error at full scale. So at 2% full scale, instrument performs at much worse, plus minus 4.8% accuracy when reading at less than half of its capacity. So this is why manufacturer only stated the limiting error at full scale. Okay, because the error is increased if the measured value is less than the full scale. Okay. So next, let's look at the ripple effect of error. Okay. So what does it mean by ripple effect or summation of error? So for example, we have two instruments, instrument A and also instrument B. Okay, and you get one output. Okay, so the problem is what happens when two or more quantities with two different limiting errors are combined. So for example, instrument A has its own limiting error and instrument B has its own limiting error, and you combine it. So what happens to the error? Okay. So for absolute error, for absolute form, okay, so it's y plus minus delta y, and for the percentage form, it is y plus minus delta y over y. Okay, so now let's look at the rules of propagation over here. So for example, we have two instruments, okay, first instrument A and instrument B. So instrument A has a value of A plus delta A or A plus percent A. Okay, so the A here is the value. This delta A here is the limiting error. Okay, so same for the percentage. For instrument B, it has its own limiting error where we have B is the value and delta B here is the limiting error. Okay, so this one is still the error, but it is in percentage. Okay, same for this one. So what happens to the error? So it depends whether the system consists of addition and subtraction or multiplication and division. Okay, so if it consists of addition and subtraction, you need to use the absolute error, meaning that you need to use this one. Okay, so this one we call as limiting error or absolute error. Error. Okay, for multiplication and division, you need to use the percentage error, which is this one. Okay, so now let's back to the addition and subtraction. So for example, if you have C is equals to A plus B, so your error, Okay, your absolute error or limiting error will become del plus minus delta A plus delta B. And if you have C equals to A minus B, then your limiting error or absolute error delta C will become plus minus delta A plus delta B. So both of these you need to add the limiting error. Okay, for the multiplication and division, okay, we will look into the percentage error. So if you have C equals to A minus B, so the percentage error C will be equals to plus minus percentage A plus percentage B. Okay, meaning that percentage error A plus percentage error B. So this is the same as C equals to A divided with B. So your percentage error C will become plus minus percent A plus percent B. Okay. So let's look at this example over here. Okay. So the first example, scenario A, is when you have a limiting error for a voltmeter is at 70 volt is 2.143%. And the limiting error for an ammeter at 80 milliampere is 2.813%. So to calculate the limiting error of power, so you know that the formula for power is P equals to VI. So V multiply with I. Okay, so it is a multiplication. So when it is multiplication, then we need to use this uh, percentage error. Okay, so to calculate for the limiting error, you need to add the percentage error. So the limiting error for power is 2.143% plus 2.813%. So it will become 4.956%. Okay, so next example, scenario B. So you have a 150 voltmeter and 100 milliampere ammeter. So both with 1% full scale accuracy. So readings for both voltmeter is 80 volt and 70 milliampere. Okay, so you are required to calculate for the limiting error. So this one I want you to try by yourself as a homework. Okay, as a homework. So this one, the voltmeter and ammeter is connected in series. Connected in series. Okay, so please try and do this example and calculate the limiting error for power. So the final answer should be equals to 3.29%. Okay. The next example, okay, this is also an example. So given the circuit like this, okay, so the current that is flowing in the circuit is equals to 2 plus minus 0.01 ampere. And the resistance is 100 plus minus 0.2 ohm. So you need to calculate the power dissipated and its limiting error. So we know that for power we can calculate using the formula P equals to I squared R. Okay, so the first thing that we need to do, we can calculate the power itself lah, the power value. So power, we can use the formula, this formula. So I is 2 ampere squared multiply with the R 100 ohm. So the power is equals to 400 watt. So this is the value for the power dissipated. Now we need to calculate for the limiting error for this power. So how to calculate for the limiting error? So the first thing that you need to do is that, remember just now we have the formula P equals to I squared R. So this formula here is actually I multiply with R. Okay, so it consists of multiplication. So for multiplication, we need to use the percentage error. However, in this question here, the error that is given is absolute error. Okay, so the first thing that you need to do is you need to convert the absolute error to percentage error. So how to convert? So the first one, let's calculate for the current. Okay, so for the current, the absolute error is 0.01 ampere, and you divide it with the current value. Okay, 2 ampere and multiply with 100%. So you will get the percentage error for current is 0.5%. The same thing for the resistance. So the error is 0.2 ohm. So divide it with 100 ohm, multiply with 100%. So you get the percentage error for the resistance is 0.2%. Okay, so now we already have the error in percentage. Okay, so now we need to combine the errors. So we know that this is I multiply with R. Okay, so for the multiplication, we need to add all the percentage error. So basically, the percentage error, the total percentage error for power will be 0.5% plus 0.5% plus 0.2%. So the final answer is 1.2%. So this is the limiting error for the power dissipated in percentage. Okay, this is in percentage. But if we want it to be in absolute error, what we can do is that we can take the percentage error 1.2%, divide with 100%, and then multiply with the power value 400 watts. So you will get the absolute error equals to 4.8 watts. So the final answer, okay, for the power and the limiting error, so if we want it to be in percentage form, it will become 400 watts plus minus 1.2%. And if you want it to be in absolute form, it will be 400 plus minus 4.8 watts. Okay, so that's basically it for chapter 2, chapter 1 part 2. Okay, so I hope that for the next class, okay, so since we have covered for power and part 2, so I want you to please do your tutorial for chapter 1, and then you need to submit it by next week. Okay, so that's all for today's class, and thank you very much.